Wireless systems differ to wireless systems in the sense that they cannot send very low frequencies through the air. And the reason is simple. We need really very large antennas to radiate efficiency low frequencies, and they are really not feasible. So in those cases, what we do is we just translate the frequency from the signal, for instance, our voice, that could be sent through a telephone wire line without difficulties, but could not be radiated to space. So we take our voice, which really has a certain bandwidth, and we just shift it to a very high frequency that could be radiated. The process of doing this is generically known as modulating a carrier wave. And here you have one example of the sinusoidal carrier wave. And it has a constant amplitude, it has a frequency, the number of cycles per second, and it has a phase. So if you want, this scale is time, and we have here the wave. Now, here we have the information. In the case of the analog, this could be just a simple tone of our voice, could be a more complex signal, but just to simplify things, let's assume this kind of slow variation. What we now do is we just change this constant amplitude, and we have the peak of the wave following this time changing signal. And what we see is just this kind of wave. The wave oscillates, but the amplitude goes up and down following the signal. This is an amplitude modulation, and is the one used in medium wave radio broadcasting. We could also do a different thing, and is to change the frequency. The frequency here is constant, and you can see this because those oscillations are all symmetric in time. They are repeating at a very constant rate. And now here, when the signal goes up, what we do is we just compress the wave. We increase the frequency. And when the signal goes down, then we expand the waveform. That means that we lower the frequency. So by just changing the frequency up and down along the signal, then we really are modulating the frequency. And this is what is done in FM radios. This was the first systems to be implemented because technically it was feasible. To extract this signal from this waveform, what we use is an envelope detector. It's just a circuit that sticks to the peak values and follows the peak values, so you recover the signal. And in the case of the radio, FM radio, we use a discriminator, which is a circuit that outputs a voltage proportional to the changes in frequency. So here we just translate the change in frequency to the amplitude and we recover the signal. With the advent of digital communication systems, things have changed, because now we no longer seek to send an exact replica of the information signal. We just digitize the signal in a certain way by sampling, quantization, and processes that are well known to you probably by now. Now, here you have a sequence of ones and zeros. We have digital bits here, and let's assume that whenever we have 1, we have a +1. Whenever we have a 0, we have a -1. With this code, we say non-return to 0 code, because you see here we keep changing only when there's a flip. But if there's no change in the bits, then we continue uniformly. And whenever there is a change here, we add 180 degrees of phase. This is a binary phase shift keying scheme. And you see the changes here. Now there's no change at this point, once again. So we introduce 180 degrees of phase changes. We represent this schematically as 1, 0 phase in a complex plane, 0, 180 degrees. And instead of using M for modulation, we use here shift keying, which is just a term borrowed from the old telegraph, which whenever the operator, usually what they did was in a Morse system, he has a key, and by on-off, by pressing the key, he could transmit the information. On those modulations, things could get more and more complicated, but here you have a simple case when we go from binary, from 2 to quaternary. And this Q could stand for quaternary for 4 symbols, or for quadrature if we modulate 2 subcarriers, one in phase and the other in quadrature of phase. But at the end, the representation is similar. What we do here now is just to use 4 symbols, which are 4 phase stages, 45 degrees, 135, and the symmetric values on a complex plane. And each one of those phase stations, here we only had 180 degrees, now here we have all the 4. Now, with those changes in phase, we associate this to a pair of bits. This is a 1, 1, 0, 1, 0, 0, 1, 0. So those 4 symbols are associated with 2 bits, and this is the way to proceed if you want to go to a higher level of modulation constellations. Now, this is just the schematic and the ideas. The mathematical representation, the basic math for these modulations is also simple. What we do is we start with a sinusoid wave, which is a continuous time wave, that is really represented by an amplitude, a sine type of dependence, could be a sine or cosine, doesn't change. And we have here an angle that changes in time. When this change in time is linear, we have just the well-defined frequency we are familiar with. And we call a carrier wave or a carrier signal. Carrier in this case in the sense that is the one that is going to transport the information. And we have the amplitude, the frequency, the angular frequency, and the phase for this wave. An amplitude modulation of this wave is just changing the amplitude in a way that is proportional to the message or the information we want to send. And information could be analog or digital. It doesn't really make any difference. What changes is the way we name them. In the analog domain, we talk about amplitude modulation. In the digital domain, we use amplitude shift keying, in the sense that we change the amplitude in discrete steps, but that's not really make any great difference. And M is representing the message or the information we want to send, and that will modulate the carrier. The other type of modulation here is the one in which we change the angle. And this is really described as angle modulation, but the angle could be changed in 2 different ways, although they are very closely related. One is by changing the frequency or changing the phase. For a frequency modulation case, what we do is we change the angle in a way that the message enters this picture in an integral form. So we add a constant factor, which is just an index of modulation related to this process, and the integral. And if you take the time derivative of the whole phase, of the whole angle here, you see this, then you will just recover the carrier frequency and an instantaneous shift in frequency that is proportional to the modulation. And this is just the scheme, the basic scheme for an frequency modulation, or an FSK, the frequency shift keying. In the case of the phase modulation, we directly change this last term here. We don't change the frequency, we just change the phase, as we did in the previous slide. And now the phase has a constant reference value, and then we add changes of phase proportional to the message, and that's the way to proceed. And those basic schemes are used in all wireless systems just to bring the information, the basic information we want to send, could be analog or digital, to a format that could be possible to be sent, radiated by the antenna and sent through the air.